Okay, thanks very much. So I'm very glad to be able to join you all virtually. And thank you to the organizers for inviting me to be part of this, and especially to Sarah for encouraging me to give a talk. So I guess my talk topic is not really so directly related to the topic of the program, but there is some amount of, well, uncertainty quantification in the sense of statistical robustness, and then some deep learning in terms of using generative adversarial networks as a computational tool. So this is joint work with my PhD student, Zheng Liu, who is just finishing up his PhD at UW-Madison in the statistics department. So let me begin with just a few words about robust estimation from the classical robust statistics literature. The goal, which was mostly formalized by Hoover in the 1960s, was to design estimators with small error, even when there were perturbations to some idealized model. So as one example, and without going into any detail at all, the idea is that if you have data which come IID from a Gaussian location family, then the optimal estimator would be the sample mean as the maximum likelihood estimator. However, if you have data that are coming IID from some epsilon contaminated model, which in the theory of Hoover means that 1 minus epsilon of the time it comes from the normal theta 1 family, and epsilon of the time it comes from a point mass located at X, then you'll see that the performance of the sample mean can be quite bad if this point mass at X is perhaps very far away from theta. Whereas using a different estimator, such as the sample median, performs much better. So this is very much a talk about what is possible in high dimensions. And in high dimensions, there's the additional challenge that even if you come up with an estimator which has optimal statistical rates, the question is how to come up with one that's computable. So I don't think I'll talk about this specifically in this talk, but when you start doing, for instance, mean estimation in higher dimensions, then one estimator that one might want to use is a Tukey median, which sort of calculates the data depth of different points and finds the deepest point and returns that. But in higher dimensions, this is computationally challenging because the computational cost tends to go exponentially with the dimensionality. Okay, so sort of as a teaser, the idea here is to use GANs as a computational tool in order to find estimators that before were very hard to find. Okay, so as I mentioned before, the usual contamination model studied in statistics is this epsilon contamination model, where 1 minus epsilon fraction of the time, the data come from a distribution F, and epsilon fraction of the time, they come from a distribution G. And one might ask, well, what sort of a contamination ball exactly is this? So it turns out that if you look at, if you let G range over all possible distributions, then these contaminated distributions lie in the total variation ball of radius epsilon around F, or if you prefer the Kolmogorov ball as well. So it's a subset of either of these neighborhoods. However, in this talk, we're going to focus on a slightly different ball of perturbations. And as mentioned in the talk title, this is the Wasserstein contamination ball. And just as maybe an illustration of this, so there might be distributions which have a small total variation distance, but a large Wasserstein distance, or a large total variation distance and small Wasserstein distance. And here are some examples. So maybe if we look at the one on the right, these are two very spiky histograms, and they're off by just a perturbation of epsilon if you were to sort of do an earth moving from one distribution to the other. But in total variation distance, it's the maximal possible total variation distance. On the other hand, if you look at the distributions on the left, well, the purple means that this is shared by both red and blue. And so because we're just putting an epsilon mass somewhere else in which these distributions disagree, then it is very small total variation distance. But it can have large Wasserstein distance if we send epsilon, the blue mass of epsilon, very, very far away. Okay, so the point is that estimators that performed well under Hoover's epsilon contamination model have no guarantee whatsoever of performing well under the Wasserstein contamination model. Okay, so here's just a brief reminder of what exactly the Wasserstein distance is. And we're not really going to go into any detail about with this formulation, but what we'll be looking at is this usual Earth mover distance in which the exponent is q equals 1, and the distance d is the L2 norm. Okay. And what we want to do is for different types of statistical estimation problems, we want to understand, well, what are some lower bounds on the rates of estimation? So in some sense, what would a good estimator want to achieve? And secondly, what are some robust estimators that have a good statistical rate and also have a computationally feasible property? Okay, so to be a little bit more precise, we'll be looking at this minimax risk, where we take an infimum over all possible estimators theta, and the supremum is now over both the location of the true parameter, so theta star, and then we take this expectation with respect to distributions p, where p is some perturbation of p theta star. Okay, so we're looking at some sort of parametric family, and the specific families will become more concrete as I go along. What we do is we generate data from some epsilon contamination Wasserstein ball around p, and we want, around p theta star, and we look at the expected loss, and we want to solve this minimax problem. Okay, so as it turns out, there hasn't actually been much work on Wasserstein contamination. So there's been lots of work and robustness on Huber's epsilon contamination model, for instance. And there was a little bit of work quite recently. So there's a group from Berkeley, Zhu, Jiao, and Steinhardt, and they looked at the same sort of robust estimation problem. And actually, in some sense, they looked at a much harder problem than we did, but they studied a slightly different, a slightly different question, a different way of quantifying what would be a good estimator. So as you'll see, the types of families of models we look at are like Gaussian location families or maybe elliptical families and so on. In their work, they looked at more general families of models, for instance, just assuming bounded kth moments. However, in their work, rather than looking at these at bounds which depend on n and p and so on, they looked at the case where you send n to infinity and you just calculate the population level risk. Furthermore, they didn't address the question of computational feasibility. Okay, so first of all, to discuss lower bounds a little bit. So there's a method that's based on the so-called modulus of continuity for obtaining lower bounds for estimation. And this was leveraged in the work of Chao Gao and co-authors for Huber's epsilon contamination. And it turns out that without too much modification, at least in spirit, the proof is very similar. One can also use this to establish lower bounds under Wasserstein contamination instead. Okay, so I'll give you the main result here. And the main result basically says that the minimax risk is lower bounded by the maximum of two things. So the first is the minimax risk if we had no contamination at all. So this is the usual parametric rate. And I'll go through some examples later. So for instance, in mean estimation for a Gaussian family, it would be square root of p over n. Then there's a second term, and this one is defined as m of epsilon theta, and we see the definition here. And we basically look at how big the loss can be when we look at two distributions that look close in the Wasserstein distance, right? So it's a supremum over theta 1 and theta 2, such that the Wasserstein distance between the two distributions p theta 1 and p theta 2 is bounded by epsilon. Okay. So as stated here, a lower bound can be obtained by taking a maximum of the usual uncontaminated parametric lower bound and the modulus of continuity. So I don't think I sketched out a proof here, but let me just do an example. So for instance, with Gaussian location estimation, if you have L2 error as your loss, then standard techniques that don't have to do with any contamination can give you a lower bound on the minimax risk. Now, what we need to do is we need to come up with, we want to calculate m of epsilon theta, which was defined on the previous slide. Or since we're coming up with a lower bound, even just a lower bound in m of epsilon theta is fine, right? And remember that m of epsilon theta is the supremum over something. So we can do something constructive. We can just come up with theta 1 and theta 2 so that the Wasserstein distance between the two distributions is bounded by epsilon and come up with some lower bound in L. And that's what we'll do. Okay, so my claim is that this m is lower bounded by epsilon. And the two distributions we'll look at are the normal theta eta 1 identity and normal eta 2 identity, such that eta 1 and eta 2 are offset by epsilon and L2 norm. Okay. And it's not too hard to see that the Wasserstein distance between these two distributions is going to be bounded by the L2 norm between eta 1 and eta 2. And therefore, these two distributions are in fact valid. So they are such that the Wasserstein distance between the two is bounded by epsilon. And if we put in eta 1 and eta 2, then we get this lower bound of epsilon. Okay, so that gives us a particular lower bound, which is written now here. And it turns out that this is actually tight. So, and that's something that can be achieved using the estimators that I'm going to discuss next. Okay, and I'll also say that I went through the details here because they were pretty easy to go through. But for different estimation problems, the main challenge in applying this theorem is to calculate what M is, right? Or some lower bound on M for different families. And in some cases that's quite easy, in others it's a little bit more difficult. Okay. So now the question is, how do we come up with upper bounds? Because then the upper bounds will tell us whether we need to potentially work a bit harder for lower bounds. So these slides can be a little bit confusing because this is more like a motivation than a very rigorous theory. I should say that for the objective function that we arrive at in another slide or two, we do have rigorous theory, right? But so the way that we're going to argue to come up with an objective function we want to optimize is we'll use this sort of so-called distributionally robust approach. So the idea is that you observe these data points x1 up to xn, and you want to figure out how to minimize some sort of distance between two distributions, where one is your estimated p theta and the other is the true p theta star, where all we know is that p theta star and pn are close in Wasserstein distance. Okay, and so for the purpose of our arguments, we're going to say, well, what if this d is exactly equal to w? We could also try to look at a slightly different distance function. So if d is equal to w, then by the triangle inequality, we can upper bound the distance between p theta star and p theta. And we can upper bound that by the distance between p theta star and pn, and the distance between pn and p theta. Furthermore, when we're looking at distributions such that p theta star and pn are within epsilon, we can replace the first term by epsilon. So instead of optimizing the original distributionally robust objective, let's say we want to optimize this Wasserstein distance between pn and p theta. Okay, so in some sense, what we're doing is some sort of a projection. We observe these points x1 up to xn, and then we want to project it back onto perhaps the closest p theta. Okay, but if you work with Wasserstein distances, you'll know that pn converges to p theta in a rather slow rate. So we want to, maybe that's on the next slide. Actually, okay, I'll get there. Okay, so for now, let's say that we want to optimize this objective function. Okay, so how do we actually do that? How would we do some sort of projection in Wasserstein distance? So here, what we're going to do is we're going to look at GANs, and since this is a workshop on deep learning, I don't really need to say much about GANs. Basically, there's a discriminator and there's a generator, and they play a game with each other. And one way of writing the objective function that a GAN is solving is this minimax formulation. And infimum over generator is G, supremum over discriminator is D, and this is the objective function. It's also rewritten in a slightly different way. So if you fix G and just optimize over the inner D, then you can rewrite this objective function as the infimum over G of the Jensen-Shannon divergence between p theta star and Q, which is the distribution of the generator. And during training, usually what you do is you don't see p theta star, so instead you look at the empirical distribution Pn and you minimize the Jensen-Shannon divergence between Pn and p theta. Okay, so the original motivation for generative adversarial networks or one of the motivations was that the generator then learns the distribution of the data. So if you want to generate more fake data, you can just learn this G and then plug in new samples of Z and generate some new images. And also in the more applied ML literature, then people actually run these GANs and they try to come up with more realistic fake images. And it was found that actually, instead of using the Jensen-Shannon divergence, if you use a slightly different, some other type of divergence, like an FGAN, then you can lead to better performance. So instead of, for instance, just generating the same copy of an image many times, you would be having a lot more variation in the images that you're generating. Towards this end, Wasserstein GANs were introduced in 2017 based on the Wasserstein distance. And the idea was that one wants to optimize this objective function where you put in a Wasserstein distance instead of Jensen-Shannon or some other F divergence. And another way of writing out what the objective function is for Wasserstein GAN is given here. Okay, so it turns out that, well, what we've done is we've gone through and reviewed what Wasserstein GANs are doing, and the objective function that we arrived at is the same as the objective function that we showed through our somewhat hand-wavy presentation earlier. Okay, so now we get to the point that I was going to mention, which is that actually, so if you study the optimum of the infimum of exactly this objective function, then the estimator that you get is not going to perform that well, even if you can actually find a global minimum of this objective function. So instead, what we want to do is we want to look at a slightly different objective function. So if I flip back to the earlier slide, the Wasserstein GAN was in fact optimizing a supremum over all Lipschitz functions with Lipschitz constant 1 of this difference between expectations. And so what we do is we now look at some subclass of these functions. All right, so instead of looking at all functions with Lipschitz constant 1, what we're going to look at is some other set D, where D is a subset of here for convenience in some of the technical details of B Lipschitz functions. All right, so really what we would do is, well, we can scale this as B Lipschitz functions and just put a 1 over B in front of everything. So the objective function that we're going to use, and so here this is where we can put aside our hand waviness if you didn't like that, and what we're going to do is we're going to exactly study the optimizer of this objective function, right? And the way that you would implement this in practice is using the Wasserstein GAN, where the discriminator is what is dictating the function class over which you're taking the inner supremum. So basically what we're going to look at is a certain subset of B Lipschitz functions, which will be defined with respect to a discriminator structure that I'll give in a moment. Okay. So I want to mention the related work that directly led to our work on this topic. It was very largely inspired by work by Chao Gao and co-authors a few years ago. And what they were doing is they were looking at the Huber epsilon contamination model. And just as I mentioned earlier, it was known for a very long time that the optimal estimators in high dimensions also seem to be computationally intractable. So they proposed using generative adversarial networks as a computational tool in order to come up with estimators in the Huber epsilon contamination robust sense. What we are doing instead in our work is we're looking at these Wasserstein epsilon contamination balls and looking at some version of Wasserstein GAN. I should say that that many of the ideas are largely inspired by Gao et al. But then the details are a little bit different, and we did have to work somewhat hard in some places in order to port over the theory from TV GANs and Huber epsilon contamination to Wasserstein. Okay, and after studying the case of location estimation, Gao et al. Also studied covariance matrix estimation, and there was some work in a paper by Wu et al. On sparse location estimation. So we studied all of these cases in our paper. Going back to the work of the group from Berkeley, Zhu, Jiao, and Steinhardt, when they were studying their question of Wasserstein contamination, they also sort of motivated the objective function that they arrived at with respect to a certain weakened Wasserstein distance. So what does this mean? Well, this is going back to the objective function that we look at, where we are changing the supremum from being over all Lipschitz functions to over a certain subclass. So there's some similarities in their approach as well. But just to underline this this one concept, so they didn't look at optimality or computational tractability. Okay, so so as I've hinted at, we need to look at a certain subclass of Lipschitz functions. Here we're letting B be our Lipschitz constant. And in particular, we're going to look at this, this structure on the discriminator. So we look at, we let the first layer have sigmoid activations where the weights have two norm bounded by B. And this is what's going to lead to the fact that things are B Lipschitz. Then we're going to have ReLU activations for the rest of the network where the L1 norm is bounded by 1. And then in the last layer, we don't have an activation, we just have a linear function. And this is because on a technical note, we want to make sure that, that a function and its negative are both in the class. Okay, and we'll let D of BL be this class of functions, just for notation. Okay. So now what we do is we want to use this to obtain some upper bounds on estimation error. And it proceeds in two parts. So the first part is a concentration inequality. And then the second part is moving this to the particular distance that we saw in our Wasserstein GAN formulation, where we're looking at an expectation of a function taken with respect to theta star and theta hat. Okay, so going back to the first part. So this is using sort of standard uniform concentration techniques via Rademacher complexity and BC dimension. And we end up with a bound that looks like this. So with high probability, we have this deviation bounded by a constant times 2 to the L times square root P over N plus the extra term that depends on the error probability. And then, well, without going into any details, if we use the triangle inequality and use the fact that theta hat is the optimal estimator, then we end up with the second equation, where we have the first term from before, and then we have an extra term that is B times epsilon over 2. Okay. So now what we need to do is we need to translate this bound that we have into an upper bound on theta hat minus theta star for specific settings. Okay, so to make this a little bit less mysterious, let's look at a particular example. So suppose we're looking at the Gaussian location family, where the true distribution is normal theta star I. Then the result that we end up with, and I'll walk you through the proof of it, is basically that that we end up with rates which match our lower bounds. So the lower bound that I derived in a slide earlier for location estimation with Wasserstein contamination was of the form max of square root P over N and epsilon. The square root P over N was the usual parametric rate without contamination, and then the epsilon came from this M of epsilon theta term that I calculated. And now we have this upper bound, and it looks similar with one issue, and this is an issue that is sort of well, it seems a bit confusing at first when you see this, but the thing is well, it depends on whether or not you treat L as a constant. So what is L? L is the number of layers in our network. And it turns out that, that the upper bound that we have actually increases with L. So in some sense, according to our theory, the upper bounds for our estimator are actually worse if we have deeper neural networks. And that's something that kind of gives you some pause, because in neural network theory, or at least in neural network practice, one often wants to use deeper networks, right? But the reason why we have an increase in L is basically that it's coming from this original concentration inequality up above. And as we know, if we're taking a soup over a larger function class, which is what's happening if you have a deeper network, then in fact the rates are going to be worse as L increases. So we sort of need to, I guess in practice, and we didn't really explore this that much in practice, but I guess in practice what you want is you want an L that's not too big so that the constant prefactor is indeed a constant. But then it needs to be big enough so that you actually find an optimum when you run this neural network algorithm to find an optimum of the W-GAN. So if we sort of let ourselves not worry too much about the 2 to the L, then in fact the upper and the lower bounds end up both being on the order of square root p over n max with epsilon. Okay, so let me try to explain to you the main steps that go into coming from this general upper bound on this sort of nasty looking expression to a particular bound on theta hat minus theta star. And again, this is where most of the technical work goes, because what we have is we have a general theorem in our paper that says the second displayed equation is true, right? But now we need to translate it into an actual deviation bound on theta hat minus theta star. So in the problem of Gaussian location estimation, what we do is we look at a specific f, right? Because we have an upper bound on the supremum over all f's in the class. And if we choose a particular f, then we can leverage that to get a bound on theta hat minus theta star. So what we do here is we look at an f, which is constructed in the following way. So basically, it's just a sigmoid applied to u transpose times x minus theta star. So what that does is in the first layer, we just need to have one of these nodes active. And then after that, we just pass everything through in the identity transformation. So we let all of the other weights be equal to 0. So this is indeed a valid function in our class. And furthermore, so what we're interested in looking at is an expectation of f of x under the different distributions. So now we plug in our f. Our f was sigma of u transpose x minus theta star. And we can write this as some other function g. So this is g of u transpose theta minus theta star. And the first term ends up being g of 0, and the second term ends up being g of u transpose theta hat minus theta star. And now the point is that this function g is locally Lipschitz around 0. So you can in turn lower bound the left-hand side by essentially the L2 norm of theta hat minus theta star. Okay, so and for the other applications that we studied, which I'll mention briefly in the slides to come, you can play similar games. So what you need to do is you need to sort of you need to carefully figure out what function you want to look at, which will give you some deviation which is related to whatever you're interested in ultimately, like L2 norm between theta hat minus theta star, or maybe spectral norm between two covariance matrices, and so on. Okay, so if you choose this cleverly enough, then you do end up with an upper bound on theta hat minus theta star in the norm of interest. Okay, so now I just want to sort of briefly mention some of the other results without saying too much about the details. I'm happy to say more if you want to ask more clarifying questions. So we looked at the case of covariance matrix estimation, and for covariance matrix estimation, at least for our upper bounds, and maybe I'll say a few words about this at the end. For our upper bounds, we need some assumptions on the spectrum of the class that we're looking at. So minimum eigenvalue is lower bounded by a constant, maximum eigenvalue is upper bounded by a constant. And just to kind of make this a little bit clearer, so the discriminator is just as I discussed earlier. But what makes it different from the location estimation problem is that when you're actually implementing this, what you're trying to do is you're trying to learn the covariance matrix. So in the earlier location estimation case, the generator is z plus some offset. You learn that offset, and that's the location estimator. In the case of covariance estimation, your generator is now going to be z times a, where a is a matrix, and the covariance matrix that you learn is going to be a times a transpose. So the theorem that we arrive at here is basically also saying that our rates that, I guess I haven't stated them, but one can find lower bounds on the spectral norm deviations, which are order of square root p over n max with epsilon, again by trying to calculate this modulus of continuity term, and one can also, using the same type of argument that I've just outlined for location estimation, come up with upper bounds, high probability upper bounds for the deviation between the spectral norm of sigma hat and sigma star. Again, we have this dependence on L, where our bounds get exponentially worse as the number of layers increase. And then well, earlier I had an assumption on the eigenvalues of sigma, And we also have some dependence on M1 and M2. So we need to assume that the upper and lower bounds on the eigenvalues are in fact constants. Okay, then we also looked at sparse estimation. So we looked at a case of sparse location estimation, where the true parameter space has an upper bound of k on the number of non-zeros of any of the vectors. Here we had to change the neural network a little bit in order to reflect the fact that we know that things are sparse. So the first layer of the neural network now doesn't just have the constraint that the L2 norm is upper bounded by B, but also that the weight vectors have at most k non-zero elements. And using a correct, or maybe a clever enough construction of an actual function that is implementable using this neural network, you can come up with an upper bound that looks something like this, where now we have a dependence on k, the sparsity, and a logarithmic dependence on p, the ambient dimension. And one can also show that this is minimax optimal by running the same procedure for calculating a lower bound via modulus of continuity. And then the last, or not the last, no, the second to the last example we looked at was structured covariance estimation, where you also want to understand if you can somehow leverage sparsity in the structure of the covariance matrix. So I think I didn't bother mentioning how we have to change the structure of our discriminator here, but let me just say that we can derive minimax rates as well. Sorry, that our Wasserstein GAN estimator can also achieve the minimax bound. Then the last application that we looked at was linear regression, where we don't have upper bounds that match the lower bounds exactly. So the last example of linear regression is where we have the xi's coming from a Gaussian family, and then the yi's conditioned on the xi's follow a regression vector beta star. And now our goal is to estimate beta star when we have slightly contaminated samples. So instead of xi, yi from p, instead of xi, yi from this linear model with sigma star and beta star, we generate them from a joint distribution P. We look at a case where we, again, restrict the parameter space so that the eigenvalues of sigma are upper and lower bounded. And we also need an L2 norm bound on beta. And we end up with an upper bound of the form order of square root P over N max with epsilon. However, the best lower bound that we were able to derive using our modulus of continuity techniques looks like P over N instead of square root of P over N. So we're not exactly sure where the gap is coming in. I mean, maybe it's just a matter of being a bit more clever in our analysis of the W-GANs, but we're not exactly sure. And maybe just to make things a little bit less mysterious, so where are all of these constraints coming in? Really, where these constraints are coming in, for instance, that the L2 norm of beta is upper bounded by some constant B1, is that back when we were trying to prove something about our the relationship between this uniform bound over all F's and here where we're trying to look at the deviations in terms of the L2 norm between theta hat and theta star. Well, at some point we need to look at a function. Here it was defined as G. It needs to be Lipschitz with a Lipschitz constant, where that, well, I mean, the Lipschitz constant will come up as a constant prefactor when we're doing this bounding. And in order to actually have a bound of the Lipschitz constant, we needed to, in the case of linear regression, put some constraints on our parameter space as we did here. Okay. I think I'm not going to talk about the experimental results because we're not really experimental people. And I mean, basically what we did was we compared our estimator with the Huber estimator when data came from the Wasserstein contamination ball, but not the Huber contamination ball. And surprisingly, the Huber estimator didn't actually do that badly for our simulations. But then we also compared it with the sample mean, and of course that did very, very badly. Maybe I'll just close with some open questions. So one thing that you're probably wondering is, well, we're using Wasserstein GANs as this computational tool in order to come up with computationally tractable estimators. However, I think there's still not that much theory on exactly how optimization goes in deep learning and in GANs in particular. So algorithmically, so even though our theory is true that if you look at the solution to this minimax problem that defines the Wasserstein GAN, you will get certain bounds on the rate of convergence of the estimator. What is still not so clear is whether when we actually run a Wasserstein GAN, when we run training for the Wasserstein GAN in practice, it is giving us a global optimum, right? So we're sort of putting our faith in that part. So the theory is fine, but the part that's not so clear is whether we're actually converging to global optimum. However, I mean, it definitely feels like a step in the right direction versus something like a Tukey median where one doesn't actually know how to calculate it in a computationally tractable manner. Some other questions are, so as I sort of hinted at when I discussed linear regression, when we were looking at upper bounds, we sort of needed to throw in a few different assumptions, for instance, an L2 upper bound on beta in the regression case, or upper and lower bounds on the eigenvalues of the covariance. That was in order to push through with our theory. It's not quite clear whether those are needed in the upper bounds. In many cases, they're not needed in the lower bounds. For linear regression, we still don't really know what the minimax optimal rate is. And then we also thought quite a bit about how to extend our linear regression story to sparse linear regression, because we could do sparse location estimation and sparse covariance estimation. But it wasn't very clear to us what we would do for sparse linear regression. All right, so I'll stop here. I'm happy to take any questions, and we're still working on getting our paper published, but it's on the archive for now. Thank you.